So we'll wait for 2 minutes, okay? ಆಮೇಲೆ ಮತ್ತೆ ಸ್ಟಾರ್ಟ್ ಮಾಡೋಣ. Okay, I think we'll start again. Is my screen visible? Can you please confirm, anyone?
Yes, sir.
Yes, sir.
Okay, great, thank you. So yeah, so previous to this sessions, we learned about uh, the architecture stack, right? So we learn what is that architecture we needed for the smart grid. So we have a physical stack, and the second one is the sensing, the communication, and then control and automation, and the application and analysis, and the last one is then the prediction, or the enterprise and the market decision making, right? So after this, like, we have seen in the depth what exactly the all three and six layers meant to us, and we spoke about what is the key component we needed in this smart grid, right? And also we spoke about the smart meters, which is very much needed to make the complete legacy system into the smart grid. And also we spoke about the actuators, which is the decision making where it will convert the digital commands into the physical, to open or close, to depends upon the load balancing and everything, right? And also we spoke about the challenges in the renewable resources what we had. So now we will talk about the stability for the variable inputs. Someone is in the lobby, hold on. Yeah, great. Fine. So let's talk about the stability. So we will be having the different variables, right? So we will be having the different input from different resources. That is, we have the solar, we have the winds, and we have the conventional time of generations, that is hydro, and so it could be in coal or else the nuclear. So there, when you merge all these resources to make a single single one, right? There will be different variable inputs which will be induced into the system. So how do we mitigate that? So let's say we have a different system for that. So let's say we have the smart inverters. So what the smart inverters will be doing is, so this the inverters will provide the voltage and the frequency support. For example, let's say we have a problem in the voltage, right? So let's say in the grid, we are facing that some voltage problem. It could be in different phases or different lines, right? So these smart inverters, what it will do is, hold on, yeah. Yeah, okay. These smart inverters, what it will do is, so these inverters will be having all the inputs we are having, right? All the inputs from our sensors, and so based on that input, this will take the decision. So whether to increase or whether to decrease the voltage or else the frequency. So when we match the exact uh, required frequency and the voltages, we can able to regulate the power quality. So that is the one thing we are actually achieving. And also these inverters can able to compensate the reactive power. So as we spoke last time, right? So the reactive power is where we have to maintain that reactive power, and it has to be in the control. So continuously we have to inject this reactive power using the capacitor banks, right? So there will be multiple capacitor banks which will be having the terminals. So these terminals will have the different variables. So these variable input can able to compensate the reactive power. So how there are different terminals, and we can call it as in different um, so it kind of the quantity of injection of the reactive power is needed. So this is can be also made it as an automated way based on this smart inverters, right? That is one thing. And when we have everything is in place, we can able to create the smart the capability, right? This is the one of the important the smart inverters uh, we have. And also the coming to the energy storage system, so this is very much needed. So this is like if you see the energy storage system, so we are having that the battery energy storage system. Let's say we have surplus energy generated. This is majorly comes into the picture where we have the PV, right? The solar. When we already have the surplus energy which has been generated, energy can be stored into the battery banks. So these battery banks, so these are all the critical for the smooth intermittency, like so these energy stored within the battery banks can be pumped to the grid wherever required. It could be unscheduled or else it could be an on demand basis. So what this will do is it will save the peak saving the even we can able to do the frequency regulations, right? And when we have these systems, let's say the smart inverters along with this the storages, we can able to manage the stable grid, right? And also we can able to have the demand the met, correct? So this is why the integration mechanism is very important. So all the components in the smart grids are smart. So when we have these systems, so what we can able to achieve is like the real time monitoring. This is very much essential for generation visibility. It is not only the generation visibility, it is also for the consumption, correct? And also based on this we can able to have the forecasting ready. So when we have these components, so the forecasting become very much easy, and also we can able to predict the load. So how much we are generating, how much we are consuming. So these are all the very much needed parameters. So these are all these the devices which help in the variable inputs, right? That is one thing. And yeah, So, coming to the decentralization. So, if you see the earlier days, it was all centralized. So, we will be having the generation, then so this will be directly to the consumers. So this is only the one way flow, right? So and also if you see, this is all centralized, it is not decentralized. For example, this generation could be in one location, and so this is not been integrated with the other generation, might be. And if it is integrated, this will be integrated with a larger scale, right? And the consumer will not have any scope to participate in this bigger generation, right? So to do this decentralization of these components, so we have the concept called the microgrids. So here the consumer also can able to participate. So when the consumer can able to participate, it is like so for example, we have the solar, the on top solar, roof solar. So let's say we are generating some energy, right? So some energy will be generating here. So initially, if you go back to the legacy days, we cannot able to pump this energy to the grid. Correct. This is the main grid, and we cannot able to do that. But now, so the technology has been so evolved, and we have the smart breakers, the smart meters. So these the surplus energy which we generate in the rooftop, it could be, or else like if we have very the smaller wind generation, so those energies can be pushed back to the grid. And also somewhere, like if we need the energy, then that can also be taken to the consumption, right? So that is the one concept, which the concept is termed as a prosumer. So when we call it as a prosumer, is where we the consumer who can able to inject the power into the grid. So when we do that, in that case we call it as an prosumers. And also, so these can be utilized for the vehicle charging or so on. It can be in many use cases for that, right? So when we are decentralizing everything, so it is called as the microgrids. So these microgrids operate individually, so it is not a centralized monitor, it is like an so decentralized way. Every household or a small facility can able to act as an individual power generation. And so these generation can be interconnected to the main utility. So this is kind of island mode, what I was mentioning earlier. These are all the independent operation which increases the resiliency. So resiliency means we are not relying on any one source. So if we have the multiple source, then we call it as an resilient. So resilient meaning is, so we are having the multiple source of resources, where if one fails, the other one will take care. In this case, we have the two source, right? The source one is the main grid, and the source two is the microgrid. So let's say the main grid fails, the microgrid can able to withstand, because we are generating the resource at the local level, and these are all not maintained centrally, it is decentralized, right? So this is how we are going to achieve the resilient in the coming future. So right now I don't see any major implementation happening, but in the coming future, this is what the technologies what we are going to implement it, right? So this is the concept called as decentralized, where the prosumers and the microgrid come into the picture. Okay. So now, operational and commercial value drivers. So when it comes to the introduction to the micro smart grids and the microgrids, what we were talking, right? So what are we going to achieve in terms of operational and commercial value, right? So there are a lot of things we can able to discuss in this introduction day, right? So one is the important one is the operational efficiency. So as we spoke, this is the key important, where we we are trying to increase our efficiency. How are we going to increase our efficiency? By reducing the technical and the commercial loss. Why technical? So as we already have complete digital data, so let's say a digital data which is stored in the database. So this database, it could be in the SCADA or else any other system, right? So this SCADA will have all the historical data, all the historical data, and that data will be stored in the DB, and these DB database can be used for the analytical purpose. Based on that, we are trying to reduce the technical as well as the commercial losses. So when we do this, so obviously we are increasing the operational efficiency, where we are trying to minimize the breakdowns, minimize the blackouts and so on, right? And also this is not only helps us in reducing technical and commercial losses, it will also help in the optimizing the asset utilization. Let's say for example, we have an uh, generation station which is underutilized, correct? So let's say it is not utilized up to its 100% value, so it is operating at 80% value the most of the time. So we can able to optimize it. Let's say either these can be able to operate at the 100% and pump the remaining the power to the main grid, or else sell to other electricity providers, right? So that is the way one we can able to do the optimization, and also everything can be automated, right? So it could be an detection and the restoration. So when we have the complete system in our database, and also it is all the real time, correct? It's all the real time. So when we have this in the real time, we can everything the system will take care. No manual intervention is required, correct? The system will detect, system will the break the circuit, all the make the circuit, and also it can able to restore to the normal operating point. So that is the efficiency, operational efficiency, what we will be achieving when we have these drivers, right? That is one thing. And the reliability, yes. So when it comes to the reliability and the resilience, we have faster outage detection, and we can able to reduce the duration and the frequency of the breakdowns, and also it will help in the self healing capability. So this is the very much important point when it comes to the operational and commercial value, right? And coming to the customer empowerment, yes, the customer can able to see the real time visibility. So they can able to see the real time data, and demand response, the participation. So basically the customer can able to participate in the demand, so he can able to see if the demand is going up or not, and if he has then micro grid, he can able to just pump the uh, his power into the main grid, so he can be able to an prosumer. So this is what we are trying to achieve. And the sustainability, yes, we have the high renewable penetration. So sustainability, where when we have the smart grids, so many of them will invest on the solar power, the wind, and basically we are trying to get rid of the coal and also the nuclear power plants, right? When we do that, so sustainability will grow, and we will be more relying on these the solar panels and the wind. So these are all the eco-friendly, so we are trying to cut down some the carbon footprints, right? So that is what it is all about. And yes, it will also improve the efficiency. So this is all about the operational and the commercial value drivers for the smart grids. So anyone has any question on this operational commercial value? Okay. So, as we spoke about the commercial and operational value, right? So it will, the smart grid, it will come with along with its own the implementation challenges and also the risk, right? So when it comes to the risk, so the main important the higher risk factor is the cyber security, right? So cyber security, why? Because so we are converting analog into the digital, right? So when we store this digital data in any of the database or else in any of the system, it is prone to attack by any of the attackers, right? So the IoTs are least secured devices in the system. So anybody has access to these specific IoTs, we call it as an endpoints, correct? We call it as an endpoints in the system. So if somebody gains the access to this specific endpoints, he can able to reach the main server. We will see how this can happen in the further sessions, but very at a very high level, this is how it will be. So if someone can able to gain the access to the IoT devices or else smart devices, he can able to breach the main server. When he can able to breach the main server, what he can able to do is he can able to switch on switch off the breakers. He can able to manipulate the complete system, right? So this is very high risk is what we have. So basically in the industrial terms we call it as an IT and OT. So OT is an operational technology. These are all the very key terms. Okay, please do remember, this is the operational technology, and IT is an information technology. So when we are designing any system, right? So IT OT converging risk is what assessment we have to do it. Let's for example, we have an any of the manufacturing unit, right? So this unit will be covered through the OT technology, not the IT. And this OT technology will be combined to the IT techno- technology will be having the database, and it has its own data center. So these IT will be always covering up to the OT. So we always have to make sure that so these IT and OT are secured. Nobody from the third party or else like any unknown person should not be able to penetrate this IT and OT. So that is very very important. This cyber security is the key risk what we have in the smart grids. And the last one is the data privacy concern. Let's say in the smart grid we are collecting the data from the consumer side also, right? Consumer side as well as the supplier side. So all the consumer details, let's say the name, their address, their information, the personal identification numbers, everything will be stored. And even the similar way, we have the supplier, his details also will be stored, and everything will be stored in the database, correct? So if we are not securing this database, this could be a centralized database or else it could be a distributed way of database. So if somebody gains the access to this database, it will be an data privacy breach, correct? He can able to sell it off. This is very high risk. uh, so whenever we design a solution, we have to make sure that how well we are securing our data. So this is very very important concept, the data privacy, and also the ITOT the convergence, and the securing the our IoT devices which is in the on field, right? So the cyber security plays in key important challenges and the risk. So in the further sessions we will see what are the technology and the protocols what we can able to use to stop the attacks and secure our databases, right? This is what we can able to do it. And coming to the complexity, so interoperability, right? So let's say we have in different vendors. For example, you might know the vendors like ABB, Snyder, and we have other big players. So they provide their own smart devices, smart meters, right? So sometimes what things will happen is we also have L&T. So these are the big players who design the smart meters, and design the sensors, and we use their components to design complete infrastructure. So sometimes we may choose the ABB smart meters and sensors, sometimes we may choose Snyder, sometimes we may choose the LNT. But the problem here is, so sometimes these two devices will not talk to each other. Why? Because this will be designed in specific the protocols, or else they have their own proprietary the softwares which will be running on these devices. The problem is when we have the multi-vendor systems, interoperability will be in very much tough. So that we have to see what is the common operating system, or else the common open source systems which can able to connect these multi-vendor systems. So let's say we have the KNX, right? So KNX is one of the technology. It is an open source. This is majorly utilized for the IoT devices. So when we have this KNX based automation system, even though we are utilizing the different vendor equipments, we can able to make them to talk to each other. So that is the one of the challenges we have. And the second challenges we have is the legacy. So if you see the BESCOM, MESCOM, so currently still they are running the legacy systems, right? So to refresh that, it requires the commercial one, and they say we cannot replace it, and it may take some time. It may take 5 years or 10 years to just to convert this legacy system into the latest one. So this is the second very much the technical complexity what we are facing it, right? And the third one is the managing the latency and the reliability. So let's say as we spoke, we have the different components in the system design, right? We have a different layers, all the layers, layer 1 to layer 6. So when we are taking the data from the layer 1, that is the physical, to the layer 6, that is the analytical layer, so there will be always some latency involved. So if we are not addressing these latencies, so we might face some delay. So delay will happen. When the delay will happen, so in that case the decision making will go down, and at a specific time the breaker may not break. So so we have to make sure that we have to create a system so that the latency is very less. Let's say in industrial standards we have a latency of 100 milliseconds, or else if we have 10 milliseconds the latency, it's really good. So to achieve this latency 100 milliseconds or 10 milliseconds, you have to choose your the components, the sensors, the switches. So it can be an IT switches, the routers, to just take the digital data to the database. So you have to design the such a way that so the latency is very less. And also we have to design a system with an reliability. Let's say you have only one sensor per meter or something. If that the sensor or the smart meter goes down, the complete infrastructure will goes down at a specific time, correct? So we have to be make sure that the reliability is achieved based on the we have to make sure that the system is completely reliable. So this is one thing. And the grid stability, so we just have to integrate the renewable resources. We saw there will be different challenges in terms of renewable integration of renewable resources, right? That is one thing. And coming to the commercial and operational risk, so this is very high cost is involved upfront. So we have to invest a lot of money to upgrade this legacy system into the what do you say, into the latest smart grids, right? So the capital is very much high. So whenever we talk about the capital, we always refer to the ROI. ROI is nothing but it's an return on investment justification, right? So let's say you are creating any smart grid and you are giving a proposal to the BESCOM or MESCOM. So they will ask, okay, we are investing so much of amount, so what will be my returns? How many years I have to wait to get the return? Let's say you are asking for an investing of the 100 crores to do the infrastructure upgrade. So the Bescom or Mescom, anybody can able to ask, so what will be the ROI, return on investment? You have to calculate in the such a way that you have to tell, okay, all the return of investment, that is the 100 crores, will be returned in the next 10 years or 15 years. So this is very longer duration, right? So this is the one of the constraint is what we are having in terms of economical challenges, right? And the second challenge is the workforce skill gaps. Right. So we spoke about the smart grid, we spoke about the security, uh, and also we spoke about the various aspects on in terms of smart grid. But do we have the skills to operate those? So let's say if you if you ask someone to design a system, they will design, but who is going to implement that system? Somebody has to configure the smart grid, correct? So we are lagging the skill gaps. So that is one of the biggest problem to implement the smart grids. Most of them, they don't know how exactly the smart grid meters will work, or else like how to configure it though. So this is the skill gaps is what we are having currently facing now. So this is the three major challenges and risk we are having in the smart grids. That is, one is cyber security, the technical complexity, and economical and operational challenges, right? So this is all about the introduction about the smart grid. So anybody has any questions here?
No,
Anyone?
sir.
All clear? Okay. So I think we only have few the participants. So this is all the slides I have for day one. So I want feedback from everyone now. So so how do we proceed? Is it okay? So as we are going with the slides and explanation, because the day two and day three will be little more technical. So I want the feedback from every one of you. So can anybody start to giving the feedback, so that it will help me also and it will help me to deliver better content to you guys.
ಸರ್ ಎವ್ರಿಥಿಂಗ್ ಇಸ್ ಗುಡ್ ಸರ್.
Okay.
ಸ್ಲೋ ಆಗಿ ಚೆನ್ನಾಗಿ ಮೂವ್ ಆಗ್ತಾ ಇದೆ.
Okay, great.
ಇದು ಮಧ್ಯದಲ್ಲಿ ನಮ್ಗೆ ಯಾವ್ದಾದ್ರು ಟಾಪಿಕ್ ಇಂಪಾರ್ಟೆಂಟ್ ಬರ್ಬೋದು, ಆ ತರ ಒಂದು ಟಾಪಿಕ್ಸ್ ಹತ್ರ.
Okay, great. Let me
ಮತ್ತೆ ಇದಕ್ಕೆ ಯಾವ